This is a quick lesson in calculus-based mechanics about how to calculate the moment of inertia using an integral. In a prior lesson, I had talked about how to calculate the moment of inertia for a uniform object. And what we saw is this depends on the mass and the shape of the object. And I had mentioned at that point in the moment of inertia basics of classical mechanics lesson that this is formally determined using integral calculus, and that's what we're going to explore more today. Just to remind you, we can find moments of inertia for multiple objects rotating at the same rate by just using the principle of superposition. We just add them all together for each individual object. I'm going to remind you that maybe if we have a hollow object, let's say we have a disk with the center missing, what we can do is we can take I1 and subtract I2 and think of this as negative mass in the center here. So that would be a strategy for finding the moment of inertia of two composite objects, one with a negative mass in theory. Also, we learned the parallel axis theorem. If we know the moment of inertia around the center of mass or any other point technically, we can just move the axis direction parallel to the original axis by just adding md squared, whatever the distance is from the original axis. So for instance, let me go back up to my donut up here. If this is the original axis of rotation here, we could move it to a point, let's say on the edge, where this would be the axis 2. I'll call this A2 and this A1. So this would be the distance D over on this. So that's how you would use the parallel axis theorem. I'm not going to use these today, but just reminding you, I grabbed this from OpenStack's college physics, a chart showing all of the moments of inertia for common objects, and we assume uniform mass distributions. And overall, what you see is that the moment of inertia is some fraction multiplied by mr squared for all of these. You can see that. But if we explore a little bit more in detail on complicated objects, and you may see my figure down here that I grabbed from OpenStack's University Physics Volume 1, is we may have some odd-shaped object where there's some sort of weird mass distribution, whether that be because of the shape of the object or because of some density distribution. It may be a uniformly shaped object, but the density is not uniform across that object. And so we can do an integral sum of the mass differentials, right? If I divide this object into a bunch of mass differentials and then integrate over r squared dm, that's how you would calculate I is r squared dm. And this makes sense what I said before. The moment of inertia is proportion mr squared. So if we just take a dm, we can do an integral sum over all those mass differentials. I'm going to remind you, you have to assign a coordinate system. Our radius is always measured from the axis of rotation. So we need to clearly define the axis of rotation. So in this situation, we can call this the z-axis, or you could call it A for the axis, whatever you want to do, and measure r from that distance. From that location. In my little bar down here, another one I grabbed from OpenStack's University Physics Volume 1. The z-axis is clearly defined here. And here is a dm, little differential. So the radius in this situation, instead of it being more like a volume integral, right, this is just a linear integral. So we need to define dm. Typically, we know mass is density times volume, and density would be some function dependent upon location x, y, and z. This could be an r theta, and then you'd want to do volume in terms of r theta, so an r dr theta. Just one R in there, sorry. But we can do it in Cartesian coordinates very easily. So remember to assign your coordinate system from which to measure all your distances. So I'm going to jump right into an example here. I grabbed this. It's a very straightforward example where we have a rod, and we're going to assume, it doesn't say in the problem that there's a uniform mass distribution, but it doesn't say that there's not. So I'm going to assume that there's a uniform mass distribution such that the linear mass density is going to be the total mass, which they call the total mass of the thin rod is m, and it has length L. So the linear mass density is just going to be m divided by L, and there's no dependence upon x here. You could be given the linear mass density as a function of x, where it could be, thin, not as heavy on this end, and then really heavy on this end. It depends on the problem you're given. But here we're just assuming a constant uniform mass density across this whole rod. I use direct integration to find the simplest expression for the moment of inertia about the axis at L equals, or the distance, the axis is found at 1/3 of the rod. So what I'm going to do, this is typical for solving these problems, is set the origin equal to 0 at this axis. Okay, so it's rotating through that axis. I'm going to set it equal to 0 there. And now we have our coordinate system. And so, we could call this the z-axis, whatever you want to call it. And then this dimension here is going to be the x dimension with positive to the right. That's a nice way to do that. So I'm going to set up the integral here. The moment of inertia is going to be the integral of r squared dm, but we're not going to do that, right? Because the r squared here, it only depends on the x direction. Like if I look at little mass dm here, it has an x location. So my integral is going to depend on x squared. The dm, this little dm, is the linear mass density multiplied by its differential length, dx. So lambda dx, we're going to put in for the dm term. Okay. When I integrate this, when I'm looking at a definite integral, I want the ends. I'm going to integrate from one end to the other end of the rod. The one end, it's located at negative 1/3 L, and the other end is located at a positive 2/3 L. Okay, so we're going to do that integral. I'm going to note that lambda is a constant, m over L. So I can bring that outside the integral, m over L, integral, negative L over 3 to 2L over 3 of x squared dx. Okay, well, if you're in calculus, that's not too bad of an integral. I'm going to add one here and divide by that result. So I get m over 3L of x cubed over the interval negative L over 3 to 2/3 L. Okay, we're going to keep going here. I don't have any comments at this point. M over 3L, let's plug in our two endpoints. 2/3 L cubed. Well, I'll get an 8 in the top, an L cubed, and a 27 in the bottom. I suppose we could leave this as a 3 cubed. It's arbitrary to me at this point. And then we're going to subtract off a negative L over 3 cubed. So we're going to get another negative sign. So I'm going to make this a positive, L cubed over 27. So when we multiply and add all this together in the parentheses, we get 9L cubed over 27. You can reduce that to a 1/3. I'm going to note that this L cancels with one of these L's. I'm left with an L squared. So overall, when we're looking at this, and we simplify, so this is a 1/3 in here, and then I multiply a 3 times a 3, so I get 1/9 M L squared. And this is consistent with what we expect for a uniform object, is that the moment of inertia is some proportion, some fraction multiplied by an mr squared on some level. So we have ml squared. And that is how you would do an definite integral with just a simple constant linear mass density.